And we are now recording and from current slide, but let me go over just a couple of additional announcements. Emmanuel's heard them, but Silva hasn't. I'll go over those, and also for people listening at home. The last 2 Fridays, I was been off campus basically completely all Fridays, both Fridays. Had treatments the Friday a week ago, not on campus at all day Friday, okay? I was at the clinic by 6:30, and didn't get out until after 4:30, so no way I was going to be on campus that day. Last Friday, I was on campus briefly twice, but that was around 6 in the morning and around almost 6 in the evening. Just for a very short period of time, exchange cars and leave. And unfortunately, this Friday, I also have my annual physical. It's supposed to start at 8, so I hope I'm first thing in the morning. Usually the doctor's not too backed up then, and usually the physical doesn't take that long, so hopefully I can get in and out within an hour, and if I'm in and out within an hour, I should be on campus by 9:45 or 10 o'clock. That's if I can get in and out in an hour. Now what happened to me, my last physical, it was supposed to be real quick like that, but I also got my flu shot at the same time. And in getting the flu shot, when she was going to throw it away, the nurse pricked her finger or something with the needle, and they called me back and had me have to do a lot of blood work to make sure that I didn't have something that she could have been exposed to. It was after she had given me the shot, so I couldn't have gotten exposed by her, but she could have gotten exposed by me. Of course, there was nothing, but it was one of those things that I had to sit and wait in line, and stuff. So I wasn't as soon back as I had planned to be. So hopefully that won't happen this time. I've already had my flu shot, and hopefully they won't want me to do my blood work after the appointment, because I'm going to go back to see my hematologist. I have to have blood work done then. I'll see if they can postpone the blood work until then, just combine it and get one stick. Usually the doctor's very good about doing that. So I'm hoping, knock on wood, that I'll get back before 10 o'clock or around 10 o'clock or so. Hopefully even earlier. So anyway, what I was getting to though, Fridays are the times when I usually catch up grading, I usually catch up Blackboard, and I usually catch up my attendance. And then I do other things as well. But those are the big things I try to get done on Fridays. Last 2 Fridays, I haven't had an opportunity. Well, take that back. I got most of that stuff done while I was in the clinic because I could use UAB's public Wi-Fi. And I got most of that kind of stuff done. This Friday, however, I was driving to Opelika, and down there we had no time and no opportunity to get any of that done. And I was so late getting back, I couldn't get it done then. I did get most of my grading done, but not all of it, but I didn't get any grades entered or stuff. So if you were looking at something on Blackboard, say, I turned this in a week ago and you still haven't got the grade up, that's why, okay? Also, I don't know if you see your attendance, but if you don't see that your attendance was posted last week, I got some of them posted, but not everything. So again, if you see that, don't panic. It's just, I hope, I've been telling people I've got 2 hours a day from 3:15 to 5:15. Hopefully I'll get things caught up by then. Since then, I've had at least 3 applications for graduation, and somebody is planning, let's see, no, I think he's already left his. So I've got those things stacked up. And I've got to arrange my field trip with my physical science class. It's got to happen this week, or else it's not going to happen because this is the end of the first mini-term. So I'll have to be tied up with that. So whereas this morning I was sort of optimistic that I'll get caught up, I'm not as optimistic anymore. But I do get to go home 5:15, and as long as not too much is stacked up there, I can do some of it from home. Maybe. We'll see. All right. Anyway, any questions on anything, but specifically Cal 3. On anything, yeah.
I wanted to see if you could put in like recommendation for honors college.
Honors college? Oh, absolutely. Just get me the information, who I need to do what to, that kind of stuff. And that's another thing. I've got one other recommendation letter pending that I've got to get out, and then I'll try to get yours. But if you give me all the information that whoever I need to send it to and that kind of stuff, I'll be glad to do that. Yeah. Yeah. Way to go. I'm glad you're considering it. Okay. Now, we were in chapter 12, vector geometry, 12.2 vectors in 3 dimensions. We had started talking about this and talked about, in general, vectors in 3 dimensions. Top of page 637, it says, no, I'm sorry. Yeah. The sphere of radius r, you see a picture of one here. Okay, excuse me. Those sneezes have loosened my head incredibly, so let me. See if I can stop the drainage somehow. Sphere of radius r, such as we have here, with center at ABC, not necessarily the origin, consists of all the points P, X, Y, Z, not just around the equator, you might see there, any point there on that sphere, located at a distance r from the point Q. The Q is the center, r is the radius. Then by the distance formula, the coordinates for that point P, X, Y, Z, that's a variable point, must satisfy this equation. Okay? Let me get my pen set up. Sorry, my voice is going on me. That distance r, good. Marcus is here. We just got one to go. If Faith gets in, we'll have perfect attendance in this class. So far, 2 for 2 today. Hopefully 3 for 3. All right, now let's think about it. We know the distance from this point PXY, wherever that point PXY is on that sphere, XYZ, is r units of distance from the center, ABC. Now, it's not necessarily the origin. So how can we write that algebraically? Well, from the distance formula, the distance between P and Q is the square root of x minus a squared plus y minus b squared plus z minus c squared. That's your distance formula, remember? And what did we say that distance was? Every point on the sphere is r units from the center. So the distance from any point x, y, z on the sphere from the center, which would be any of those points there, any of those distances there, that is always equal to r. Okay? They actually put the r on the other side, so I'll do that now. Now, what you could do, what do you think you could do to maybe simplify this a little bit? Anything? What don't you like about the way that equation looks? What's the nastiest looking thing about it? The square root. And how do we clear a square root? Square both sides. So I'll do it the way they did. X minus a squared plus y minus b squared. Now they didn't quite do it like this, so I'm going to do it plus z minus c squared is equal to r squared. Squared both sides. Now, if you restricted yourself, now I'll allow this to the xy plane. Let's say of the, well, not the XY plane. The XY plane that's parallel to the plane that's parallel to the XY plane, but C units above that XY plane. So in other words, say the XY plane was here, your sphere is up here. Let's come C units up until you're exactly at the equator of that sphere, and then you're at Z is equal to C, so this term goes away. Now you're describing a circle, a minus x minus a squared plus y minus b squared is equal to r squared. That would be the circle they've shown here. The only thing they didn't say was let's have this point be at xyc. You have that plane where the xy varies, but the z is always constant. Okay, and if you did that, then you would have the equation of this zero. Now, why they did that, I'm not sure, but that's the next equation they did, and here it is. Okay. Now, I'm sure there's a reason, and I'm sure they'll get to that reason, but for now, it's not real clear why they did that. Okay. So they said, consider that equation in the xy plane. And in reference to what they were saying earlier, I would say parallel to the xy plane where z is equal to c. If they said that, that would be perfectly fine. They didn't say it that way, but it's fine. Okay. However, as an equation in R3, it defines a right circular cylinder of radius r whose central axis is the vertical axis. So this is actually talking about a different figure. Okay? Oh, I see what they're saying. What we did before, we stopped right there. New topic. Okay. New topic is now consider this equation. Okay? And this is in the xy plane, and that would be a circle in the xy plane of radius r. But if you said, no, this is a three-dimensional, you're on R3, then you would have to let that circle rise or fall as far as it wanted to. In other words, now you define the sphere, a cylinder, a right circular cylinder in 3 space that has an axis parallel to the z-axis. Okay? In fact, it would be the z-axis the way they've written it here. No, not necessarily. A and B don't have to be z. Okay. So, yeah. Now, it actually seems like a lot of blah, blah, blah. Here's what they're getting around to, okay? And this, I guess, is all you really need to know. I was going to go through this faster, so I shouldn't have been trying to explain everything, all the rationale. Here's the equation for a sphere in R3 of radius r centered at Q equal ABC. Just the same as what we just did. X minus a squared plus y minus b squared plus z minus c squared is equal to r squared. Exactly what we derived. That's exactly the same formula. Now, I want to do one more thing. Okay? Sorry about this. I also want to divide everything on both sides of the equation by r squared. Ding, 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 ding. We got perfect attendance. Way to go. 3 out of 3 classes so far today. Excellent. Good to see you here. And we'll divide this one by r squared. And we'll divide this one by r squared. Okay? So there is yet another formula. X minus a squared over r squared plus y minus b squared over r squared plus z minus c squared over r squared is equal to 1. Okay? Now, that r squared doesn't have to be r. It could be anything, you know. as long as it's the same under each of the terms, and each of these terms has the same coefficient for your variable, and there's a 1 over here. If all these are the same, I wouldn't use A, B, or C. That's typically used, but because we used them up there, we won't. But say B squared or M squared or anything squared, these three are the same, these coefficients are the same, and that's equal to 1. That's also, I consider that the standard form, rather than this one. That's standard also, but this just says any equation of a sphere is this one. You can divide by r squared. That to me is more of the standard equation for a sphere in R3. Okay? An equation of right circular cylinder in R3, that's three-dimensional space, of radius r. Now a cylinder, the radius is always in one plane or another, okay? Because a cylinder in the third dimension doesn't have a radius. It has a height in that dimension. Whose central axis is a vertical line through AB0, then that equation will be the one we see here. X minus a squared plus y minus b squared is equal to r squared. Now that vertical line is going to be parallel to the z-axis, but not necessarily the z-axis. Okay? Now, doing the same thing we did before, you can divide everything on both sides of this by r squared as well. And then you'll have x minus a squared. And oh, here's another way you can write this. I should have done it up here. X minus a over r squared. I could have done that same thing up here. Plus y minus b over r squared. Same thing you could have done up here is equal to 1. Okay? That would give you the same thing. A little more of a standard form. Okay? Especially when you get to other shapes. So I just wanted you to introduce you to a couple of those. By the time we get to 12.6, you'll see why I'm putting these other forms in there for you. Okay, let's do example 1. Okay, let's just read it. All of you got books? Yeah, okay. Describe the set of points defined by the following conditions. Okay, I think I'll erase everything on the slide. No, I hit the wrong button. Okay. The following conditions. X squared plus y squared plus z squared is equal to 4. And it says here y is greater than or equal to 0. It's a pretty ugly y, isn't it? Okay, you don't have to agree so quickly. Okay. All right. What is that describing? Look at all like either one of those two equations we have there. Which one? Say again? Yes, it definitely looks spherish, doesn't it? Now, what's the difference between this equation and that equation? Okay, the center of this is at origin, not at A, B, C, because you don't see an A here, you don't see a B there, you don't see a C there, so we assume those are 0. If you're at 0, 0, 0, the center is the origin. What would be your R? 2, okay, because R squared is 4. But what does that condition on the side tell you? Okay. In other words, it's a hemisphere. Okay, half a sphere, because your y, whichever way it's pointing, usually we have x pointing one way, y pointing another way, and z going up. But whichever way the y is pointing, you only have that half of it. The x and the z's are fine everywhere. The the y is only positive. And since this is at the origin and y is only positive, you're only going outward on the y-axis. X and z goes on both positive and negative, but y is only outward. So that would be a hemisphere of radius 2. What you might also say to describe it, it's on the, makes a circle on the xz plane, okay? Because the xz plane is the plane that can go positive or negative. The y is just here, so the hemisphere is only, whichever orientation you make for y, that would be what you got. Okay, very nice. Nicely done. The B one. X minus 3 squared plus y minus 2 squared is equal to 1. But the condition they have here is that z is greater than or equal to negative 1. All right, what does that give you? A cylinder. Okay, anything special about the cylinder? Okay, the radius of the circle is that defines that cylinder is 1. What else do you know about it? Okay, it's translated. What do you mean by that? Move to the new center of 3, 2. Exactly, 3, 2. What else do you know? You pretty much beat the left-hand side to death. What about the right-hand side of the comma? What does that tell you?
Starts at -1.
Okay, yeah, it has a base. Z is equal to -1 and stands up from there. So let's just say this is my x-axis, that's my y-axis, this is my z-axis. You've gone 3 units out here on x. Let's say there's 1, 2, 3, and gone 2 units over here on y. Here, that's where you've centered the circle, but you've gone down 1 unit below into the subflooring here, and that circle has radius 1 going from there up, parallel to the z-axis, but not on the z-axis. Okay, very good. Did a good job of that too. Starts 1 unit below the xy axis and goes up from there, but not down. Very good. Okay. Here's the, whoa. They only showed the picture of the second one. Why didn't they show the picture of the first one? Okay, I guess in the old book, they didn't show the hemisphere. Is that right? It has both. I don't know why this one doesn't. But there is your right circular cylinder on the xy plane. Okay, it's right there. This is 1 unit south of there. Right circular cylinder centered at, I guess this is centered at AB. This may be, okay. Ah, that's right. That's the one that shows it going infinitely up and down. Okay. That was the one that went with the second equation here. Second equation here equal r squared. That's what you got. All right, here's the hemisphere. Okay. I hadn't gone far enough in my slides. Okay. So this shows if x plane is coming out this way, x-axis here, y-axis there, z-axis up, right-hand rule, that works. But y is greater than or equal to 0, so you cut it off at the xy plane and have a hemisphere sticking out of there. Okay? X and z can both be positive or negative. Y can only be positive. And then here is the second one. Yours has, 3, 2, that's right, isn't it? 3, 2 is 3 on the x, but only 2 on the y. Doesn't look like that's quite dimensionally correct. It looks like that's almost a square the way I'm looking at it. It really shouldn't be. This side's longer and that side's a little shorter. Then that is the center, but going down to -1, and that would be your base circle, and then it goes up parallel to the z-axis from there, a radius of 1. So this goes from y is equal to 1 here, 3 there, 2 is here, y is equal to 2 on this edge, y is equal to 4 on this edge. I mean, x equals 2 on this edge, 2 on this edge, and the center is 3. And then the center is dropped down to a -5. And then the radius of 1 also r squared is 1. All right, good deal. Now, let's move back to vector concepts. We sort of stopped and did a little analytic geometry. Let's go back to vectors. And we're going to kind of be tying the two together. As the plane, as in the plane, the vector v, which is PQ, let me see. We'll use this as long as we can. When we have to write, we'll have to do it. Here's the vector v, which is also PQ, but now this one's in 3 space, R3, is determined by the initial point P down here. They're showing this at 332, and the terminal point Q up here at 574. Now, again, looking at our axes at home, understand this. You're drawing a 3-dimensional figure on a 2-dimensional board. There's going to be problems, okay? Things will not always be like they seem. Okay, the first was 3, 3, 2. Okay, that gives you your initial point. Okay, now, again here, it looks like the x-axis is foreshortened a little bit, and the y-axis is then a little bit extended. Z-axis is more like the y, but less like the x. So it just depends on how they orient these things. It's hard to get a real true picture of what it is. But that's 332. Because frankly, to me, even though that looks approximately the same as that, of course, more than that, oh yeah, I'm sorry, I was looking at the wrong one. This 3 looks more like that too, but this 3 is longer than that too, so that's how it should be. But you see, this is down coming toward you, so you can't get that third dimension in there all that well. You're then going to point Q, which is 5 units on X, 7 units on Y, and 4 units up. At least it's twice as far up as what that was. Okay, there is a terminal point. Now this point is coming out like this. It doesn't look that long here. It looks like it's in the YZ plane. It's not. You know, that's the thing. You get no third dimensional perception. Okay, because you're on a 2-dimensional plane. Okay, so but there's what we got. That point, PQ. Now, then they go back to talking as if P is some arbitrary point, A1, B1, B1, C1, that's P rather than 332, and Q is some A2, B2, C2, some other point there. Then the length or the magnitude of that vector V is denoted by, just like we did before, if this is vector V, I can't write on it. Okay, so this is vector V, then the magnitude of that vector V, anyone want to hazard a guess? Anyone? Second? Oh, you did? Okay, what does it say? A2 minus A1 squared plus B2 minus B1 squared plus C2 minus C1 squared. All that is on your square root. That's your magnitude of V. Notice it's not a vector, it's a scalar. It's a length. A positive length, because we're taking a principal square root. Okay? Now, notice here it doesn't matter when we talk about the length. The direction that matters, which is listed first and which is listed second. But the length of it, it didn't matter. You could have done this minus that. That's perfectly fine. In fact, you could have, I don't recommend it, done them any order you want to, as long as you keep x's together, y's together, and z's together. Doesn't matter which way you do, because the difference of them is going to be plus or minus of each other, depending on which one you put first, and you're squaring it, so you're going to get the same value and adding those together. So that is your magnitude of those vectors. Okay? In this case, it would have been 2 squared is 4 plus 25, that would be 16. Wait, that's not right, is it? 2 squared is 4 plus 4 squared is 16, that would be 20. And then I know the 2 squared. Did you say 24 or 25? Huh? Oh, I thought someone said something. Okay, sorry. That would be 2 squared is 4 plus 4 squared is 16, and 4 plus 16 is 20, plus another 2 squared, another 4, that would be the square root of 24. That would be the distance between those 2 points. Of course, the square root of 24, you could simplify that a little bit by saying 2 root 6, right? Yeah, because square root of 24 is square root of 4 times the square root of 6, and square root of 4 is 2, so 2 root 6. Okay? Root 6 is what you drive to that note. Okay. Now, okay. All the terminology and the basic properties discussed in the previous section carry over to R3 with very little change. Okay? And Emmanuel's already used the word. A vector V is said to undergo a translation if it is moved without changing its direction or magnitude. But now you can move it in 3 space. So if this is a vector like here, okay, like that, you can move it anywhere you want to in 3 space, even behind the boards, wherever, as long as you don't change the magnitude nor the direction. That would be a translation. Okay, you use that when you were talking about moving the center of the circle from the origin to AB before. Okay? 2 vectors, let's see if they have these written down. Yeah, well, there's an illustration of it. 2 vectors V and W are equivalent if W is a translate of V. Okay? Now, I don't really like to use the word a translate. I notice this book does. To me, the translate is a verb. Okay? But I don't know what else to use. A translocation, that would be a noun. Or even just a translation seems better, but they call it a translate. If W is a translate of V, that is, if V and W have the same length and same directions, they're translates of each other. So these 2 vectors here, vector V and its translate based at the origin. Okay? So if this is your original vector V, just anywhere out here, components A, B, C. Notice the angle bracket indicates those are components of the vector, A, B, C. Now, if you translate that, now that could be, they make it seem like it's in the XY plane. If that was in the XY plane, this would be A, B, 0. But if C is still let it to be variable here, or other than 0, then that would have to be elevated or reduced, but it would have to be somewhere there. But then you move it to V0, the translate of that, where you have the same magnitude. Since the origin is the initial end now, the upper point is going to be ABC. Now, those are coordinates of a point. These are components of a vector, and when you move it to the origin, where A minus 0, B minus 0, C minus 0. That gives you the coordinates of a point where Q0 would be located, okay? When it's based at the origin. Okay, two non-zero vectors V and W are parallel if V is equal to lambda W for some scalar lambda, okay? So what that means, if, well, this doesn't have to be at the origin, but let's just imagine it's somewhere, and this one is the same magnitude but shorter length, or longer length, but same direction, okay? Then that would be parallel line. Certainly any translate is parallel to itself because it's in the same direction, but it has the same length. A parallel vector only requires it to be in the same direction without being the same, necessarily being the same length. But they have to be non-zero, okay? Now, excuse me. The position vector of a point Q0 is the vector V0, which is equal to the origin to Q0 based on the origin. Yeah. So again, this is a translate of that here, where this is vector ABC in 3 dimensions. This was also vector in 3 dimensions, but guaranteed that the foot be on the I swear I've got a sneeze again. All right. I may have to go clear my head, but let's see if we can keep that. Where the initial point is the origin, then that makes the QB ABC, coordinates ABC. What point was that trying to make? Oh, the position vector would then, they say this is a translate located at the origin, later they call it position vector, okay? Those are the same things, okay? If its initial point is at the origin, then it's a position vector. A vector V, PQ, with ordinates A, B, C, that would be the one out here in front, is equivalent to a vector V0 at the origin, based on the origin, based at the origin. Goodness, I keep saying the same thing over and over, with Q0 equal ABC. How many different ways they're going to say it is the same deal. The components of V, which is also PQ, where P is A1, B1, C1, and Q is A2, B2, C2, are the differences of those values. If this was at A1, A2, A1, B1, C1, this was at A2, B2, C2, then A here would be the difference in A1, A2 minus A1. Now this time the minus sign does matter. Remember when we were using the distance formula, it didn't matter, you're squaring anyway. But now it does matter. It's always the terminal point minus the initial point. Always. So A2 minus A1 is your A, B2 minus B1 is the C, C2 minus B2, C1 is the C. Okay? All right. All right. Let's do a little example here. What if P were the point? It's not this P here, I'll warn you, okay, not that one. If P is the point 3 minus 4 minus 4, okay, Q is the point, goodness gracious, I can hardly breathe. 2, 5 minus 1, Okay. Then you tell me what vector V is in component notation. Say that a little louder. The P is the initial point, Q is the terminal point. -1, comma. Nine, comma. Yeah, 3, comma. 3 close angle bracket. Yeah. Yeah. Okay. Got it. Now, two vectors are equivalent if and only if they have the same components, which means they are translates of each other. Okay. They don't have to be translated in the standard position, but they just are moved to some other position. So any two vectors with the same components, they are equivalent vectors. Okay. Okay. Vector addition and scalar multiplication are defined as in the two-dimensional case. Vector addition is defined by the parallelogram law, except now it's a parallelepiped law or something like that. Okay. Okay. In terms of components, if vector V is equal to V1, V2, V3, vector W is W1, W2, and W3, then, well, let's see, I think they have this on the slide. Yeah, they do. Okay. Let's go back to this one. This is the parallelogram law of vectors in three space. All right. So let's say you have a vector coming out here some way. It's hard to see whether that's below the on or above that XZ plane. It's just hard to see. Okay? And you've got another vector W back here that appears to be coming out from the YZ plane, XZ plane. Hard to see where it is in relation to the other, but at least it appears it may be actually on this side. It's hard to see. If you added these two vectors together and in other words, put this into that one, or this one into that one, then you're going to get a vector V plus W. Now, I said you might feel like it should be parallelepiped rule. That would be if you were adding 3 or more vectors. 2 or more will always define a plane. It won't be the XY plane or XZ plane or YZ plane, but it will define a plane. The plane that contains these two vectors will also contain the sum of the vectors, because this has only got components here, this one's only got components there. However it does, wherever they're going or changing, they still define a plane that is made up of the two. So it is still a parallelogram rule as long as you're only adding 2 vectors. You're adding a third vector that wasn't in that same plane, now you're got more something like we did at the very beginning where you form a box of some nature of parallelepiped, 3-dimensional box. Okay? Now, that was vector addition defined by the parallelogram law when you've only got 2 dimensions. 2 vectors, I'm sorry. All right, now this is where we were. Oh man, leaving off before. Okay. Now, let's say you have a vector v in free space, a1, a2, b1, c1, and you multiply that by some scalar lambda. Okay. This book is using lambda a lot here, where a lot of other books will use. One reason you wouldn't use a C is you've got a C1 here. You don't want to confuse those. But it could be a K. This will like to use lambda. Fine, no problem. Well, lambda times the vector v would be a new vector along the same line as a1, b1, c1, just with the scalar lambda scaling it, either lengthening each of these or shortening each of these. If lambda is a number, and it's just a number, just a real number greater than 1, then this vector is along the same direction as a1, b1, c1. It just goes further. Okay? Or if lambda is between 0 and 1, then this would be a shorter vector, but also along the same line as a1, b1, c1. Now, if lambda happens to be negative, then it just fires it in the opposite direction. Okay? And then the magnitude of lambda would be how far it fires it. Lambda's magnitude is between 0 and 1, then it just fires a short distance in the opposite direction. If it's greater than 1, it is a longer vector, but in the opposite direction. Okay, so that was your scalar multiplication. Your vector addition would be if you have vector v plus w, and again, so you only have 2 of them, then, well, I mean, even if you have more than 2, when you're dealing with component notations, just add the components, the corresponding components. And here you're not limited to having just 2 vectors or 2 dimensions. You can go 3 vectors, 3 dimensions, or 17 vectors in 3 dimensions, okay? You just add the component a1 plus b1, that'll be your new first component of the sum vector. b1 plus b2 would be the second component of that sum vector. And c1 plus c2 is the third component, z direction of that vector there. Okay, just like we showed before, that just gets you in the plane. The sum vector is in the same plane as vector v and w defined. Okay. Now, vector addition is commutative, associative, and satisfies the distributive properties with respect to scalar multiplication, which we saw in Theorem 1 in the last section. Remember, not all the things you can do. You cannot we haven't talked about how to do a distributive property with respect to vector multiplication because we haven't defined vector multiplication yet. I'm trying to think of a good way to say that. So let's look at example 2. I don't think this is a picture of it. It may be. Calculate the magnitude of V. So things we're looking for first is magnitude of V. Okay. And 6V minus 1/2 W. Where V is equal to 3, -1, 2. Oh, put my vector signs here. Where vector V is 3, negative 1, 2. Okay. And W, four, 6, negative 8. Okay, I think I've written them first. Yeah. Okay. Then determine whether V and W are parallel. We'll do that later. Okay? We'll talk about that in a minute. So first, let's calculate magnitude of V. What would be the magnitude of V for this V up here? This V. What is the magnitude of that? The square root of 3 squared plus negative 1 squared plus 2 squared. That would be, okay, I couldn't hear. Square root of, okay, that was, oh, I see what you're doing. Well, not sure either. 9 plus 1 plus is a squared 4. Yeah, 14. Okay, I understand what you're saying. I thought you were saying 40, I thought. Okay, 14. Square root of 14. Nothing much we can do to simplify that. It is a scalar. It's a number. It has no direction. It has no components. It's a number. Square root of 14. Okay. Now, it says determine or calculate 6V minus 1/2 W. What would that be? Okay. Goodness gracious, I can't read my writing there. The pen must be skipping. Okay. What would this be? $18, comma, negative 6, comma, 12, plus 2, 3. I think it's a negative 8, isn't it? Oh, yeah, wait. Yeah, negative, okay. Yeah, negative 4, yeah. I was so worried about the sign, I forgot about the magnitude. Okay. And then if you add those two together, what do you get? Say again? Is that a negative 2? Oh, I'm sorry. It's a 1/2, it's a minus 1/2, I'm sorry. I put it as a plus. It's up there and I didn't see that. We're doing a minus here. Okay. So you're right, this would be, whoops, that's not right. Okay. That would be a 16, comma, I can't hear. Okay. Minus 6, right? Minus a 3. Negative 9. Okay. And okay, I didn't hear. You may have said it, but I didn't hear. I can't get. What's the third component? I can't get it to erase that. Okay. What's the third component? 18. Okay. No, is it? Okay. 12 plus 4. 16. I think. I mean, if I'm reading it right, sometimes my writing gets a little sloppy, very sloppy. Yeah, 16, negative 9, 16. Very good. Now, it asks if V and W are parallel. Determine whether V and W are parallel. Okay? Now, remember what the requirement for parallel vectors would be. There must, goodness gracious, there must be a common scalar that would equate them. Okay? The common scalar you would have between these would be 4/3 or 3/4. That one would be 6 or something like that. That would be a plus or minus 4, a negative 4, negative 6 and negative 4. There's not a common factor between all those. So no, they cannot be parallel with each other, because there would have to be a common lambda that you could multiply by each of the terms to get the other set of terms. Okay. Now, we're going back to, and this is where this figure comes in. I don't think we need this anymore. I don't think any one of those is that. Okay. So let me erase all these. Goodness gracious. Let's see if we can talk through this. It's probably not centered well, but it's okay. The standard basis vectors in R3 are very similar to what they were in R2, except in R2 they were just I and J. In R3 they're I, J, and K. I is the unit vector along the x-axis, J is the unit vector along the y-axis, K is the unit vector along the z-axis. So we could write any old vector V, which we could write as A units out here on I on the x-axis, B units on the J, and C units up here. We could write that as the vector, angle bracket, A comma B comma C, close angle bracket. Or we could write it as AI plus BJ plus CK. So if you don't like using the angle brackets for that terminology, then just write it IJ and K. You put the same components in there you would otherwise. So any vector ABC is the same as AI plus BJ plus CK. Okay. If you go theoretically to 4 or more dimensions, then same thing holds. You just can't draw pictures of it any longer. And even your 3-dimensional picture is hard to get the exact gist of this, except in this one you know you're in what I would call the first octet here. So this is coming out of the board like that, not back there anywhere else, because it indicates A seems to be positive, B seems to be positive, C seems to be positive. And so they're going along the basic axes. That's enough said about that, I guess. All right. Now, every vector is a linear combination of the standard basis vectors I, J, and K. So, if you wanted to write this same expression here, of course I'm going to have to reduce it. Yeah. That would, I don't know why the pen's not right. Oh, there we go. Vector V here you could express as A times, and vector I is 1, 0, 0, plus B times vector J is 0, 1, 0, plus C times the K component, K unit vector, which would be 0, 0, 1. Okay, and if you, by the way, these should be, I wrote them as if they're points. These should be angle brackets here because those are vectors. So this would then be A, because A times 1 is A, the other two add the 0, comma, B, comma, C, angle bracket. Okay. So that gets you right back where you started. Or AI plus BJ plus CK. So, I don't know if this is beneficial to you or not. It's so simple, but let's do it. Write this in another way. -9, -4, 17. In accordance to the standard basis vectors, what would that be? -9i minus 4j plus 17k. Okay. Whoa. Goodness gracious, where did that come from? $17K. Okay. I guess the hat took off and went somewhere. Okay. All right, let's do example 3 then. Now, we're going back to another concept here. What do we mean by E sub V? I'm going to put some symbols over it so it'll hint you what is E sub V. Okay. You were starting it pretty well, I thought. Well, when I put the hat on it, what does that indicate to you? I do this, the book doesn't. That indicates it's a unit vector. Certainly I, J, and K are unit vectors, because 1, 0, 0, 0, 1, 0, 0, 0, 1. Those are unit vectors. So this is a unit vector in the direction of the vector V. Vector V, notice here, has an arrow over it. It's any old vector. Could be longer than the unit vector, shorter than the unit vector. The E sub V would be the unit vector in the same direction as V. Okay? Now let's do that for 3-dimensional vectors like vector V. And how do they give it? They give it in IJK components. 3i plus 2j minus 4k. Okay. What would be your unit vector in the direction of that vector V? Goodness gracious. What would you have to do? Okay. Get the magnitude of V, which would be the square root of 3 squared squared. Okay. Which would be square root of 9 plus 4 plus 16. So this would be the square root of 29. Absolutely right. What do we do with that? Why did we do that? Say again? That's what we divide the vector V by. So in other words, divide each of these by the square root of 29. The square root of 29. The square root of 29. Okay. So there would be E sub B. It would be the vector V divided by the magnitude of vector V. That's a short and dirty way to say it. This would be vector V divided by the magnitude of vector V. Okay? In other words, determine the magnitude, divide each of the terms by that. And if you don't believe me that that is a unit vector, obviously it's the same direction because we multiplied this vector by a scalar, 1 over root 29. That's a scalar, right? Same scalar times each term, that makes it a parallel vector scaled up or down. If you dividing by a number greater than 1, that's scaling it down. So the other requirement would be that the magnitude be 1, where if you take this squared, that would be 27 over 29, 9 over 29, plus 4 over 29, plus 16 over 29, that would be 29 over 29. Sure enough, that would be a unit vector. Okay, that's 1. Okay. And there we have it. I wrote it in IJK components because that's how they started. But in vector components, what would that be? Three over root 29, comma, 2 over root 29, comma, negative 4 over root 29. Close angle bracket. All right, does that make sense? Now, IJK, those indicate vectors. Okay, these indicate numbers, and you got to tell what those numbers represent. Components if it's angle bracket, coordinates if it's parentheses. But the vectors out from unit vectors, they're there. Okay. 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 But, okay, when they pull the 1 over the square root of 29 out, is that what you mean? Then that's a parenthesis there, 3i plus 2j minus 4k. Okay. Now, see, this carries with it the vector characteristic. This means you're just multiplying the scalar by each of those terms. So something has to say, this is a vector, okay? And if you don't have unit vectors or things like that, you use angle brackets, saying these are components of the vector. When you already have the vector characteristic intrinsically there because you're adding 3, and by the way, these are orthogonal vectors. They have no components in the same direction, I, J, and K, that are all perpendicular to each other. So you just go somewhere on I, somewhere on J, somewhere on K, adding those together. This is your vector, shows you this is a vector because it's made up of components of vectors, and this is just a scalar out front that gets it back down to a unit vector length. All right. Now the next thing we're going to talk about, the parametric equations of a line. Now we're kind of, in a sense, I feel like it's just kind of jumping kind of all over the place, okay? Parametric equations we talked about already. Lines and shapes and other things we've talked about. Now we're kind of combining the two of them together. Okay, and what we've got here, although the basic vector concepts in 2 and 3 dimensions are essentially the same, there is an important difference in the ways lines are described in parametric equations. A line in R2 is defined by a single linear equation like y is equal to mx plus b. Equation of a line in slope-intercept form, sort of a standard kind of form. Okay, when you get to 3 dimensions, that's not an easy concept because you have a vector going up here. What is the slope of that? What are you referring the slope from or to? There is no change of y over change of x. You got change of z over both changes in x's and y's, and yeah, there's no simple concept like that. Okay, so what they do in 3 dimension, a single linear equation defines a plane rather than a line. A single linear equation defines a plane rather than a line. Okay, now here's how I think about it. That may not be the best way to do it. If your space is 2 space, a plane, then a single equation will define a quantity 1-dimensional less than that, a line. A single equation will define line. When you're up here in 3 space, a single equation defines a plane. Now, it may not be one of the axis planes, but it defines some plane. So when you see an equation in 2 space, it's just, in 3 space, just an equation there, you've just defined the plane. Now, we haven't talked about how to do that yet, so don't let that bog you down yet. It just is a plane. If you saw something, well, we'll describe that later. A single linear equation defines a plane rather than a line. Therefore, we describe lines in 3 space in parametric form. Okay. Now, first, we're going to deal with, note that a line, that's a strange-looking L. I don't know what that is. A italicized L0? I don't know. It's just a strange-looking shape. That's not quite a capital lambda, I don't think. Maybe it is a capital lambda or something. Through the origin consists of multiples of non-zero vector v. Okay? So in other words, here's this line L, L0. Okay? Now a line doesn't have a fixed length. Okay? It goes infinitely in both directions. That's a line. Okay? No fixed length. A line segment has a fixed length. An array is fixed on one side with the other infinite. A line, though, is defined to be infinite in both directions. Array infinite in one dimension, and a line segment terminating in both positions. So here we have a vector v. Okay? If you have another vector they're calling r sub 0, and by the way, vector v is initiating at the origin, by the way. Okay? And let's say you have another vector r0 as a function of t, then that t can be any scalar multiplied by v. Certainly, if t was 0, you're going to have the 0 vector, which is just the point of the origin. It is a point. Okay. But any t other than 0, like anything less than 1, it's going to point somewhere up here, something less than v, okay, depending on how small the t is. Any t greater than 1 will then continue up here. So this shows this one for one value of t. Looks like it might be a little bit more than 2, okay? A little bit more than twice the length of t. If t happens to be negative, then you go down this way, okay? So then the line through the origin is some multiple of v. In other words, it's a parametric equation times a vector v. And the t can take on all real numbers. Negative, positive, small, large, whatever. That's going to give you line L0. Can't ever deviate from that because you're multiplying by that direction v, whatever the direction was there. All right, so that's one example of a line, L0. Now that's one coming from the origin. Now, what if we have, and they do one more thing here, and let me write it down. Oops, I can't. I'll have to shrink it and then write it down. This TV here would then be T, this is so small. Okay. All right. If V were, this is an assumption here, this V, vector V, are components A, B, C. And then this T times V would be the vector TA, TB, TC. Now you could write the T at the other end, AT, PT, CT. It doesn't matter. I'm just doing it the same way they did. And by the way, for this to be the line L0, anywhere up and down there, T can be any number. I guess they don't put equal signs under that, do they? They shouldn't. Yeah. Okay. Okay. Any number greater than negative infinity and less than positive infinity. For all real number T's, that's that line L0. Okay. Now, what if you had another line? There's your TV, there's your TV, just like we had before, but you have a line that's parallel to that one. In the same direction of V, but not through the origin. Okay. Now, they put P0 here. That 0 doesn't mean it's a line through the origin. What it means is a point measured from the origin. So many units in X, plus or minus, I can't tell which that is. So many in Y, it looks like those are positive, and so many in Z, it looks like it's got to be positive. So this is going to have some component X1, Y1, or X0, Y0, Z0. That will give you the point P0. Okay? Now, if you take the line of P0 from the origin to P0 and add to that your line TV, then by your parallelism rule, now that we're looking at it this way, you just add this to here, and now you get the line L. I assume that's a capital line. Okay? Now think about what that's saying. This line is parallel to V, okay, but not the same length as V. It says infinite length, so then it's going to be some parameter times V. That means it's parallel to it, but it goes through a point P0, so you offset this by the vector OP0. Okay? R of T here is the green line L, or lambda, whatever that is. And it's the OP offset from the origin. That's the line that it goes through, and then plus TP. All right. So that's how we designate a line as a parametric equation. Now, there are a few other things we can do with that, okay? All right, let's go back to this for a moment then. This point here, as I said, was X0, Y0, Z0. So that line isn't necessarily going to go through the origin. The one down here is. The lambda 0 does come from the origin, or go through the origin. This one does not necessarily. Okay? So if you're doing this, that would be your R of T, that represents the line, parametric equation for a line, would be this vector, and now because that is measured from the origin, then that vector has the same components that the point has coordinates. So that would be x0, y0, z0 plus t times v, but that was your ta, comma, tb, comma, tc, okay? Which you could then express as x0 plus ta, comma, y0 plus tb, comma, z0 plus tc. Okay, so those are all different ways you can refer to that line. And I guess one more that you could do, x0, y0, z0 plus t times a, b, c. Okay, now written in that form, that would be the vector from the origin to P0 plus t times the vector v. Because remember, a, b, c was just the vector v. So this would be your point off the origin, okay, x0, y0, z0, that the line's got to go through, plus the parametric equation, t times the vector v, ab. Okay. So, have we beat that to death? All right. What's the takeaway here? Here are ways you can express the equations of a line in point direction form. Point being point P0, direction being the vector V. The line, lambda, or whatever that funny looking symbol is there, through the point P0, now that's a point, so that's parentheses, x0, y0, z0, close parentheses. In the direction of vector V, that's vector ABC, is described in this vector parameterization, which is the OP0 vector, the vector from the origin to this point P0. And since it's coming from the origin, these coordinates here become the components there. That gives you your offset, and then this gives you your direction, okay? And the t lets you go plus, minus, short, long, whatever, okay? Now, the parametric equation, this is the vector parameterization, okay, is written this way. R of t is this. Your parametric equations would be x equals x0 plus ta, y is equal y0 plus tb, and z0, z component would be z0 plus tc. Okay. Now, in this sense, the parameter t varies from negative infinity to positive infinity to give you an infinite line through that point. Does that kind of make sense? Wow, how did that happen? Okay, let's see where we'll start next time. We'll start on example 4, I think. Okay. All right. Let's see how far we didn't get to, not much further we had to finish. In homework exercises here, do either 1 or 3 or both, 5 or 7 or both, 9 or 11 or both, 13, do 13, it's the only one like that. Then do either 15 or 17 or both, any of the odds 19 to 23, either 25 or 27 or both, either 29 or 31 or both, any of the odds 33 to 39. Okay, now wait, I'll let you stop somewhere in there. Okay, if you can do 33 through 39, go for it. If not, wait and we'll finish this later. I would say, yeah, let's wait and finish it later. You probably can do 33, and you probably can do 35. You can try it if you'd like to. You might be able to do 37, but you can stop somewhere in that frame, and we'll pick up and go from there. All right, good deal. Just a quick reminder, this week is the last week of the first mini-term, meaning we're approaching midterm, and I would love to have either your research paper in or your first test in before next week. And the reason I say that, they sometimes ask for samples of student writing. No, they sometimes ask for, what do they call that? Midterm progress reports that week after midterm. So if you can, I mean, if you don't finish it this week, finish one or the other over the weekend. So I'll have some sort of a grade for you. So when they ask for midterm progress report, I won't put down, you haven't done anything. Yeah, because I know you've been doing something. So try to get at least either the paper or the first test in by next Monday, if possible.
You just go to the Boston State website, and then under current students on Honors College, it says recommendations.
Okay.
You just fill it out.
Okay. All right, great. Okay, now is that under the this current student, is that under student suite or faculty suite or something?
No, it's just if you go to the Boston State,
Right.
there's a little box that says current student.
Current student?
Yeah.
Never seen that.
Yeah, just go there. Let me see if I can find it. Right here it says current student.
Oh, wow. Well, I guess I have seen it, but I didn't know what that was talking about.
You click on that, it says Honors College,
Okay, yeah.
and then all the way down there's recommendations.
Okay, great. Thank you.
Thank you.
Like I say, do you know if there's a deadline on that?
Yeah. I think it's we have to have the recommendations in before we do interviews, and the deadline for the interviews is the 10th of March.
They want to finish them by the 10th of March or start
The interviews. And
Yeah.
we have to have the recommendations before that.
before the 10th of March. Is that right? Is that what you're saying? Okay. All right. That gives me about 2 weeks. So I've got to get Matthew's done, and then I'll get yours done.
Yeah, I think I looked at it, and it's not long.
Right, yeah.
Do a lot of writing.
So is there a form?
Yeah, it's
So it's not a recommendation letter.
No,
It's just,
it's not.
okay, right. Got it. That's it. Yeah. Okay. We'll try to get that done hopefully this week.
Okay, thank you.
Okay.